Good morning, guys. I hope you are having a great day.
Good morning.
Good morning. Yeah. Okay. Before I start this class, I would like to introduce myself again. My name is Laksh, and I work for Cisco now for the past 3 years, and I have an overall experience of 9 years, mainly for the routing and switching side, basically the wired side. And I have majorly worked with majority of the Indian telecom giants like Airtel and Jio, Tatacom, etc. And outside India also, I have worked with many clients as well. So I completed my CCNA back in 2015. I completed CCNP route and switch as well. And last year I attempted the CCI service provider. However, I could not attempt it. So I'll be attempting it again in the month of May this year. I also have a CCNP specialist certification in enterprise core and SP core both. So yeah, so I'll start with the class now. But before I move on into the class, I just wanted to know, is there anyone who has completed CCNA here, or who has completed CCNA and is working on CCNP completion right now? Please give a raise of hand. If you mention it on the chat, I may not be able to see the chat right now. Just give a raise of hand. Okay. And anyone else, though they do not have the CCNA certification, uh, uh, how much level of knowledge, let's say in the networking, how much do you rate yourself out of, is there anyone who rates himself or herself above 5 in networking? Above 5 or 6 or 7, whatever, between 5 to 10. Is there anyone who says that I know a lot of things? So before we begin, let's just start with few questions, so that I am aware of the level at which I should be training you guys. Okay, I see few people who have raised their hand that they have completed CCNA. The rest of them, I believe, you have not completed CCNA and you have directly jumped to CCNP. Okay, fine. So let's start. What I'll do is, let me ask one question. Okay, first thing, can you tell me what is the how does ping work if I ping from router 1 to router 2? Let's say there are two routers. Okay, let me share my screen. There are two routers, router 1 and router 2. Okay, router 1 and router 2. The router 1's loopback address is 1.1.1.1 and R2's loopback address is 2.2.2.2. The interface IP here is 12.0.0.1 and here the interface IP is 12.0.0.2. So if I do a ping, ping 2.2.2.2, okay, what will happen? Can anyone tell me the step-by-step process of what happens if I do a ping from R1 to R2? I need a step-by-step process of it.
First, it will send a hello packet.
Okay, first it sends a hello packet. Okay.
Then it will get the replay for that. The ARP table is there in the same IP. It will get the replay.
Okay, so it is sending hello for what?
For the IP address.
It is sending hello for the IP address. Okay, and then the second step.
It will get the replay whether that MAC address is there already in this.
Okay, so what the process that you're telling, what do you call that process?
Handshake.
Handshake. Okay, handshake for?
Getting the IP.
Okay, handshake to get the IP. Okay, this is a statement, but what do you call this process? All right. Anyone else would like to? I'll come back to this. Anyone else would like to tell me the step-by-step process of what and how does a ping work?
Yeah, hi, this is Vishal.
Yeah.
Okay, so assuming that router 1 and router 2 have the routing entries for reaching both these IPs in the routing
Which
table,
IPs?
these 2.2.2 in router 1 and 1.1.1 in router 2.
Okay.
Okay,
Hmm.
so in that case, router 1 will send an echo packet, and yeah, which is an ICMP, which uses ICMP.
Okay.
Yeah, and the router 2 will, in response, will reply back with the echo reply.
All right. So, okay, one last attempt. Anyone else?
Yeah, so my concern is that so first of all, router one when we will ping route from router one to router two 2.2.2, then router one will check its ARP table,
Okay.
and in that ARP table it check the whether I have the MAC address of this IP or not.
Okay.
So if the MAC address is present, so he will directly send the packet to the destination. And if the MAC address of the destination 2.2 is not present in his ARP table, then he will try to find, and to find that MAC address, he will send that packet through the gateway.
Okay. Okay. So I believe that these two responses are almost right. Okay. So if we combine these two responses, right? So we'll get the proper working of ping. So let's start how basically a ping works. That's first question. Okay. So uh, when I do a ping, okay, when I do a ping from R1 to 2.2.2.2, okay, first thing, as someone had pointed out, R1 should know, okay, let me instead of writing, let me write. R1 should know how to reach 2.2.2.2. Okay, why? Because 2.2.2.2 is not directly connected. It is not directly connected to R1. It is directly connected to R2. So if I just simply do a ping to 2.2.2.2, it's not going to work, because in R1's routing table, in R1's route table, an entry should be there. Entry for 2.2.2.2 should be present. Then only it can, first of all, start a ping to 2.2.2.2. Now let us assume that the entry is there for 2.2.2 in its routing table. Okay. So that entry can be through static routing, or it can be through a dynamic routing, like if you created OSPF or EIGRP or any kind of dynamic routing protocol which shares their information, right? So now R1 knows how to reach 2.2.2.2. Okay. The second thing, first, this is the first. Second thing that happens is, once we do a ping, okay, so what happens? There is a, okay, one more thing. When I do a ping, what first it creates a layer 3 header. First, it creates a layer 3 header with a source IP and a destination IP, right? The destination IP here is 2.2.2.2. Can someone tell me what will be the source IP? Can someone tell me what will be the source IP here?
12.0.0.1.
12.0.0.1. How?
Because
You're
this is
right,
the
but how?
interface IP.
Okay, if it is the interface IP, why should that be the IP address?
I mean, if we did not give any source while trying to ping, in that case, it will consider the interface IP, the highest interface IP.
Because this is the exit gateway, right? So that's why.
Yes, yes, yes. That's the right. So what happens? As I said, it needs an entry to reach 2.2.2.2. Okay, first thing. After that, what it does, it checks in its routing table how to reach 2.2.2.2. In its routing table, there might be an entry which says to reach 2.2.2.2. Okay, use the exit interface. Use the exit interface or use the next hop IP. Right? These are the two possibilities. Use the exit interface or the next hop IP. Right? Let's assume that it's using the exit interface. Now what happens? The exit interface, let's say that this is fast Ethernet 0/0 or any kind of interface, whatever you want to assume it. Fast Ethernet 0/0. This fast Ethernet 0/0 will have an IP address. And that IP address, according to our diagram, is 12.0.0.1. And that is why it chooses the exit interface IP address as the source IP address. So instead of, if I write ping 2.2.2.2 and I mention source as 1.1.1.1, then only here the source IP will become as 1.1.1.1. Otherwise, it will be the exit interface IP address. And now we know why the exit interface IP address is chosen. Okay. Then second thing, layer 3 header is created. There are other things also in the layer 3 IPv4 that is created. I'm not writing all those things, right? Then in layer 2, it needs the source MAC. The source MAC will be this exit interface MAC address. I'm assuming it as 1111. Okay, 1111 means all digits are 1. Now it needs the destination MAC address. Correct? With the destination MAC address, what happens? Let's assume that it does not know the destination MAC address for 2.2.2.2. Right? So what happens? It keeps this as a sideline. Okay. Please mute yourself. Everyone, please mute yourself. So it sidelines this ICMP packet that it has generated here. Okay, Internet Control Message Protocol. Ping is a type of ICMP protocol. Okay, it sidelines this. Then it creates an ARP packet that someone has pointed out. It creates an ARP packet. In the ARP packet also, it has format. ARP has a format. Okay, it has ARP is a layer 3 packet. Okay, ARP is a layer 3 packet. In the layer 3 packet, it then fills those headers. The first header is the source IP, where the source IP is 12.0.0.1. The destination IP is 2.2.2.2. Right? Then the source MAC. Source MAC, I'm assuming it is all ones. Then the destination MAC. When in the ARP, can anyone tell me what will be the destination MAC in the ARP?
First time it's all F.
No.
All zeros.
Correct. It's all zeros. It is all 0, and it will say that this is an ARP request. And I think the ARP request value is, I think it is 0, 8. I think it is 1 and 2, if I'm not wrong. The ARP request value is, I think, is 1. Okay, I'll check that. Okay, so that request, this is ARP request. Then this is a layer 3 packet. Then a layer 2 packet is again created, where the source MAC is 1111. When I'm saying layer 2 packet, it's an Ethernet header that I'm talking about. Okay, then after that, the destination MAC. Here, the destination MAC is the broadcast address, FFFF. So this is your layer, this is your ARP packet that has been created. Okay, this gets sent to R2. When it reaches R2, first what R2 does is R2 checks the destination MAC. It sees that it's a broadcast MAC address, And in your layer 2 header, there is a field called type field, which tells what kind of layer 3 information is it carrying, right? So here it will be mentioned as ARP. That gets pointed out. So obviously, if R2 wants to know for whom this ARP packet is destined for, it needs to open the layer 3 packet. When it opens the layer 3 packet, it sees that the destination IP is 2.2.2.2, which R2 already knows that it's directly connected to me. It's the loopback address for myself. Okay. And 2.2.2.2, then it also knows that it's an ARP request which is coming from 12.0.0.1, right? So now R2 knows that some guy whose IP address is 12.0.0.1 with a source MAC 1111 is requesting, has sent me an ARP request, right? Now I need to give him a response, ARP response, right? So ARP response, it turns the value to 2. I'll confirm this values 1 and 2. I'll just confirm. I'm getting confused between the values of ICMP echo and ICMP echo, ICMP request and ICMP reply, and the ARP request and ARP reply. I'm getting confused between the values of these two, but I'll confirm. So when it is sending the ARP reply, right, all these values gets changed. Wherein here the source IP is again 2.2.2.2. The destination IP is 12.0.0.1. Source MAC is R2's MAC address 2222. I'm assuming destination MAC is 1111, right? And then in your layer 2 header, the source MAC is 2222. That is R2's MAC address. Destination MAC is R1's MAC address. Type again is ARP field, right? This then is sent towards R1. R1 opens first, sees the layer 2 header. It sees that the destination MAC is its own MAC address, okay, its interface MAC address, and it sees that the type is ARP. Now, what kind of ARP is it? Is it an ARP request, reply? It needs to find it out. If it needs to find out, it needs to open the layer 3 header. When it opens the layer 3 header, it sees that the destination MAC is its own interface IP. The IP address is 12.0.0.1, and it's an ARP reply. So it knows that some guy whose IP address is 2.2.2.2 with a source MAC of 22222 has responded for his ARP request. So now with all these values, the ICMP header that was incomplete without the destination MAC is now complete, where the destination MAC has the value 2222. So this is your ICMP request that is being generated now, which is complete. When it is complete, when that is complete, it is sent towards R2, right? What R2 does? R2 first checks the destination MAC, which is 2222. It accepts it. Then in the type field, it sees that it is an IPv4 packet. What kind of IPv4 packet is it? There are many types of okay, it is an IPv4 packet. Now I need to open the IPv4 packet. When it opens the IPv4 packet, it sees that the destination IP is 2222, which is directly connected to it. It's the loopback address, and it's coming from 12.0.0.1. And in the layer 3 header, there is another field called protocol field, which the ICMP packet, basically first an ICMP packet is generated. This ICMP packet is encapsulated inside your IPv4 packet. The IPv4 packet is then encapsulated inside the layer 2 Ethernet header. So first R2 reads the layer 2 header, then it reads the IPv4 header. Inside the IPv4 header, it sees the ICMP packet. Inside the ICMP packet, it sees all these information, where the destination IP is 2222, source IP is 12.0.0.1, and the ICMP request value, I think, is 0. Okay, ICMP echo value is 0, right? So when it is responding back, it responds with a value of 8, right? And all these values gets reversed. The source IP becomes 2222. Destination IP is 12.0.0.1. Protocol field says it's an ICMP packet. In the source MAC, it says it's 2222. Destination MAC is 1111. The type field remains IPv4, and this packet is then sent back to R1. So this is how your ping basically works. So whenever someone asks you the step-by-step process, you need to tell them this. There is no need to go in such a depth, but if you know if you know in depth how it works, you'll be able to. The moment you start explaining, the interviewer will get an impression that okay, everything he knows how ping works, and with that, not just ping, you have explained how ARP works as well. What is the ARP format? What is the ICMP format? You have mentioned all those things. All right. One more question, and we'll get into the course. How many of you are comfortable with OSPF? Like whenever you go into the interview, first they think, do you know OSPF? Are you comfortable with OSPF? Okay, just with a show of hands, tell me how many of you are comfortable with OSPF? All right, no problem. So I'll ask this question. In the OSPF adjacency formation, OSPF, first question, what is the difference between OSPF neighborship and OSPF adjacency? Can anyone tell me what's the difference between
Adjacency,
neighborship and adjacency?
Sorry, neighborship means they exchange the hello packets. Okay. And bidirectional visibility is confirmed. OSPF adjacent, suppose two routers, R1 and R2 are neighbors, means they exchange the hello packets and bidirectional visibility is confirmed. Okay. But adjacency means they both come to the full state and the link state database are synchronized. So then in that case, they both are adjacent.
Okay. Anyone else? What is the difference between neighborship and adjacency?
It will exchange routing updates with adjacency only. With neighbor, it will not exchange routing updates.
Okay.
When it will routing updates will be exchanged, then it will call adjacent only.
Fine, no problem. Anyone else? Last attempt. Anyone else? Anyone else would like to give it a shot?
Yeah, neighbors are two OSPF routers sitting in, I mean, on the same segment, let's say, or hear each other, but they do not exchange any routing information. They are called as adjacent when they share routing information.
I think most of you got that right. So when we say two routers are OSPF neighbors, that means they have just exchanged their hello messages. They have two routers have exchanged their hello messages. Okay, sorry. This is R1 and R2. They have exchanged hello messages. In their hello messages, they have just exchanged with their router IDs. Okay, and they have agreed to they have agreed upon their hello timers, dead timers, areas, etc. And they are in the same subnet. They have agreed upon that. So that is where your neighborship comes. Now, with the neighborship, when they are OSPF neighbors, at what OSPF stage are they? What is their OSPF state in their in their neighborship? What's the OSPF state when they are neighbors?
Two-way state.
Correct. They become two-way. They are in the two-way state. So till your two-way state, the routers are called as OSPF neighbors, right? After this only, they start to exchange their database information, right? And the database
DVD information only.
Sorry?
Only DBD, only
Yeah, yeah, yeah.
DBD packets they will exchange.
DBD is a summary of your database descriptors, right? So that is why I use the term database. Anyway, so the exchange of your database starts at the X start state. Okay, after your two-way state is the X start state. Second question, what happens in the X start state? Can anyone tell me?
An X start state, first master and slave will be selected. I mean, who will start the exchange fast? That will be selected, and that will be based on the router ID. Okay, whose router ID is highest, he will be master, and he will start sending DBD packet.
Okay, anything else? Anyone else would like to add what happens in the X start state?
In this state, there is election between the master for the selection of master and slave, whose
Okay.
router ID is more is selected as a master, and
Okay.
router ID is less. This is selected as slave.
Okay. Anything else?
In this state, they are extracting the information like they have this IP. Do you know about this? So they are extracting the information, exchanging the information.
Okay. Take that as well. Exchange of information. Okay. So as you, yeah, someone is saying anything?
Yeah, they will not start exchanging. They will just start exchanging the DBDs in this layer, in this stage. And I think in um, the TR and BTR is also elected in this stage. If it is those are in the broadcast, in same broadcast.
Okay. Yeah. So I'm not coming to the DBD, DR concept right now. So most of you got this right, that they elect master and slave along, and whoever has a higher router ID becomes the master, the other becomes the slave, right? Along with this, not just your master and slave, along with this, your MTU has to be same. This is also there. If R1 and R2 do not have the same MTU, okay, there will be an error thrown that the MTU there is an MTU mismatch, and the R1 and R2 both will be stuck at the X start state. Okay, so MTU has to be same on both ends. If you do not want the MTUs to be negotiated, right, you can disable MTU negotiation as well. So R1 and R2 will not check for MTU mismatch. That's one. Second thing, the sequence number of DBD is also decided. If it's a master and slave election is happening, they also decide on the sequence, the starting sequence number, right? The starting sequence number of the DBD with which the master and slave will start to exchange the DBDs. That's okay. So first thing, master and slave are elected, MTU is negotiated, and the starting sequence of the DBDs are also agreed upon. The next, as you guys have said, there will be no exchange whatsoever. There will be no exchange in the X start state. The name itself says it's the starting of exchange. It has not yet started. It's going to start. It's the start of the exchange. The next state after this is your exchange state. Here only your DBDs are basically exchanged between the master and the slave. All right. Once the DBDs are exchanged, they go into the loading state. This is where they synchronize. This is where they exchange their LSAs, right? Exchange their LSA with link state updates and link state acknowledgements. They come to know about each other's database in full, and then they go in the full state. When they are in the full state, that's when the two routers are called as adjacent. Okay, till then they are not adjacent, they are just neighbors. Even with the neighbors, they are only in the two-way state and not in the adjacent state. Okay, any question here? Anyone? All right. So someone is having trouble getting my voice. Is everyone able to hear me clearly?
Yes, I can.
Yes,
Yes.
it's
All right.
clear.
Thank you. Yeah, thank you. No problem. Okay. So with this, I hope you get how how my teaching style is, how in depth do I go in these things. All right. So we'll start with today's lecture. Before we move on, do anyone of you have any questions regarding the two questions that we discussed just now?
Yeah, I want to know, like, since let's say we are trying to explain about the ICMP, how it's going to be exchanged, right? When we're doing the ping, how that works. So yeah, after that explaining, can we do the live demo? It should be easier to like understand thoroughly, like what we see on the theory and then how that happened to the live.
Yeah, no problem. I mean, this was from just an interview point of view, but if you want,
Mhm.
I can show that right now as well. It's okay. So whatever practical that I will be doing is on two softwares. One is called as the Cisco Packet Tracer, which I'm pretty sure most of you are aware of, and second is the GNS3. Okay, in the GNS3, I will be mostly performing bigger or advanced routing technologies. Sometimes Cisco Packet Tracer does not have the capability to do advanced routing. Okay, so even you will be shocked to know that MPLS cannot be performed on the Cisco Packet Tracer. Okay, so
So you will not be using the networking lab.
So guys, that all the topology is already there in our lab, so you can access that also. That there is no difference in all.
Okay, cool. Yeah, sure.
Yeah.
all right, sorry about that. So let me show you. Let's take the example of two PCs. Okay, two PCs connected with a switch here, and just we'll do a ping. I hope the diagram is not too small. Let me zoom in. Right. This is PC number 2. Okay, so I'll give this PC an IP of 10.0.0.2. Okay, and it automatically chooses the subnet mask. We'll discuss about the subnet mask in our later classes as well. And this is 10.0.0.1. Okay, so that's it. All I need to do now is in simulation, let me show you what happens. I'll try to ping from PC1, that's on the right hand side, to PC2. PC1's IP address is 10.0.0.1. So if anyone wants to make a note of it, please do. Okay. Or let me just write it down here. Give me a minute. Let that application open. This is 10.0.0.1 and this is 10.0.0.2. All right. And let's check what's the MAC address that it has assigned itself. I'll take the last four digits of the MAC address, that is 4BE6. Okay. Okay. No. That's not the MAC address. I'm sorry. There's a link local address. Okay, generated something. Let's check what is that. See here what it did. I did not do anything. I did not do a ping. It generated an ARP. If you see here, it generated an ARP. But this is basically a gratuitous ARP. Okay, it is basically a gratuitous ARP. Okay, which the difference between a gratuitous ARP and a regular ARP is that when a regular ARP is generated, where I, or here in this case PC1 is when it is trying to reach a destination IP, that's when it is generating the ARP. But here, without even asking or without even getting someone's ARP reply or request or anything, it's generating the ARP on itself. That means it's called as the gratuitous ARP. Okay, the spelling is GRATI gratu. Yeah, gratuitous ARP. Okay, that means it's saying that my IP address is 10.0.0.1 and my MAC address here it's 4BE6. That's my MAC address. It's already populating, or it's it's broadcasting its MAC address on its own. So now in this case, if I do a ping from PC number 2 to PC number 1, it will not generate an ARP. Why? Because PC1 has already sent out its own MAC address and the IP address that it belongs to. So now if I do a ping from PC2 to PC1, there will be no ARP generated before ICMP request. A ping will go directly. Okay, since it has already generated the ARP, I cannot stop it. Okay, so let it go. We'll see what happens. Everyone clear with the gratuitous ARP? Right. So this is 4BE6, and if I just simply play this out, okay, this reaches the switch. What does the switch do? Switch first sees for switch, it reads the MAC address, destination MAC address, that is all broadcast, all F, right? And since it's a broadcast address, it needs to send it out of all the ports except the port that it received on. And as per our diagram, there's just one single exit port. So it will forward it to PC number 2. PC number 2 will receive this gratuitous ARP. Okay, gratuitous ARP, which says that this is the source address. Okay, and this is the source IP. So now it already now knows the MAC address for PC number 1. All right. Now let's see that if I just simply do a ping from PC number 2 to PC number 1, ping 10.0.0.1, we received a reply from PC number 1. Had there been no ARP request or gratuitous ARP generated by PC1 or PC2 earlier, we will see a small gap here. It would say request timed out. Okay, whenever it says a request timed out, it means that there is an ARP, there is an ARP generated and there is an ARP resolution going on. Okay, once the ARP resolution completes, we'll start seeing replies. So the first will always be a request timed out, and then we'll start seeing the replies. But here, since PC1 already broadcasted its own MAC address, PC2 now knows the MAC address for 10.0.0.1, and it did not have to create an ARP request. Okay, so let's see this again in simulation mode. In the simulation mode for Cisco Packet Tracer, we can see the packet level information step by step of what's going on. So please bear in mind, I'm pinging from PC number 2 to PC number 1. Okay, so here it has generated an ICMP packet. It has generated an ICMP packet. So if you remember, I mentioned your ICMP packet. Okay, your ICMP packet is encapsulated or covered inside your IPv4 packet. Your IPv4 packet is then encapsulated inside your Ethernet packet. So you have 3 layers inside. It's just not that layer 2, layer 3, layer 4. No, inside layer 3 itself, you have another encapsulation. ICMP itself is a layer 3 packet, right? And IPv4. To understand this better, what is an ICMP and what is an IP. How do you see this in real time? Just imagine that your IPs, okay, IP, be it an this as the roads in our real time. These are the roads that you see: ICMP, ARP, OSPF, EIGRP, or any kind of protocol that you think of are the vehicles. Okay, so you have different kinds of road. You have a road. You have you can say that you have a 4-lane road, that is IP. You can drive ICMP, you can drive ARP, you can drive OSPF. It's upon your requirement. So similarly here, so similarly in this case, okay, this ICMP is basically, okay, driven over an IPv4 road. Okay, and your IPv4 road is then being encapsulated inside an Ethernet layer. All right, so if you see here, it says that the destination MAC is 4BE6. How it knows that? Because of the gratuitous ARP that PC number 1 sent it. That's why it already knows the destination MAC of the destination IP. It has mentioned its own source IP 480D. 480D. Okay, that's the source MAC. Now, inside the IPv4 header, it has mentioned the source IP, that is 10.0.0.2. Destination IP is 10.0.0.1. Okay, you will see this is the version field which says it's an IPv4. Okay, and then yeah, that's all for now. That's all we know. And here is the protocol field. Inside this protocol field, it says this is an ICMP. That value is 0x01. That's the value of your ICMP. So if you open the ICMP, we will see those ICMP values. This is an ICMP request. The ICMP request value is 08. 0x08 is the ICMP value. So please make note of that. The value is 0x08. All right. Then what happens? This packet is sent to the switch. Switch now sees the switch. Now it has received a MAC address, right? Destination MAC address 4BE6. Switch checks in its MAC address table. Let's open switch's MAC address table. So we'll see that it says 4BE6. 4BE6, any MAC address ending with 4BE6 can be reached out of port number fast Ethernet 0/2. So how switches learn MAC address is going to be our discussion as well. Okay, for fast Ethernet 0/2. So if it needs to reach 4BE6, the packet has to be sent out of fast Ethernet 0/2, and the switch forwards the packet to PC number 1. PC number 1 receives this packet. It sees that the inbound detail. In the inbound detail, it will see yeah. So in the inbound detail, it will see the MAC address is destined for PC number 2. Then it says that the type field says 0800. That is the value for IPv4. What kind of IPv4 is it? What kind of information is this IPv4 carrying? If I need to know that, I need to open the IPv4 header. It opens the IPv4 header. It sees the source IP. It sees the destination IP, that is its own IP address. And in the protocol field, it sees ICMP. So what kind of ICMP packet is it? It sees that it's a request. So the request is for me, that is my IP address, right? It's an ICMP request. Then I need to respond to this ICMP request. If I need to respond to this ICMP request, all these fields get reversed. The destination MAC becomes PC1's PC2's MAC address. This is PC1's MAC address. Source IP is PC1's source IP. So destination IP is PC2's MAC IP. In the ICMP header, the value, the ICMP response value is 0. So your request ICMP request value is 8. ICMP response value is 0. Okay, so that is confirmed now. Request value is 8. Response value is 0. And then what happens? PC2 now responds back. Sorry, PC1 switch again. It looks for 480D, right? 480D. If it needs to reach 480D, it has to send the packet out of fast Ethernet 0/1, right? So it sends the packet out of fast Ethernet 0/1 and reaches PC2. So PC2 now has received the ICMP response for the request that it sent, right? So if you see here, the first reply for the request that it sent has been received. So if I do that in the real time here, we'll see 4 requests being sent and 4 responses being received. So packet sent is 4, received is 4. There is no loss of packets, right? So it's 100% reception. Any question with this? I see people have raised their hands. Okay.
I just wanted
Kaushik,
to confirm,
let me just go one by one. Kaushik, yeah, I see that you have raised your hand. I'll come by one. I'll come.
Well, I raised long time back. Okay, I did not raise hand right now. Thanks.
All right, no problem. No problem. So you can lower your hand. It's okay. Aziz. Okay, Aziz has also done. Jitisha. Yes, Jitisha.
Hello, sir. I just
Yes.
wanted to know which version of this Cisco Packet Tracer you're using.
Let me just check about. This is version 8.2. Yeah, I'm not using it. It's just the latest version that I downloaded from the Cisco site. It's a free free software. You can go to the Cisco site. Okay, let me show you that as well. Give me a minute.
Actually, I have got version 7 in my laptop, so that is why I was thinking like this is, I think, better version than the 7. That is why.
No, it will still work. It will still work. I mean, I think when you log into the Cisco Packet Tracer, it will you to it will pop. So here it says that download for free, right? Download for free, download and get started, all these things. So all you need to do is you need to create your Cisco login credentials. Once you create Cisco login credentials, you need to watch these videos before you start using it. Once you watch these videos, you will be able to freely use the Cisco Packet Tracer. Okay. There are something on the chat as well. Okay. So this is about our ICMP.
Hi, sir.
Okay. So, yes, please
this is Vishal.
say out your name so that I can.
Yeah,
Yes,
so
Vishal.
correct me if I'm wrong. Can we say Ethernet 2 as in road, IP as in vehicle, and the protocols that it is carrying as in the passengers?
From OSI layer point of view, yes. from OSI. Okay, no, you cannot say that as well. Okay, the reason, I'm sorry. The reason is that if we look into the TCP/IP suite or the OSI layer model, okay, you have layer 7, layer 6, 5, 4, 3, 2, and 1. One is your physical layer. One is your physical layer. This is our data link layer or Ethernet layer, right? This is network layer, transport layer, transport layer. This is our session, presentation, and application, right? So we cannot say that data is a road, network is vehicle, transport is passengers. No, because your passengers are also carrying data from the application layer as well. Okay, so it basically depends upon the kind of application that you're using. So if it's just the communication, if the communication is just between two routers, if the communication is just between two routers who are not involved anything other than who do not have any involvement of above your transport layer. Okay, then in that case you can say data is your road, network is your vehicle, transport layer is your data. You can call that. Okay,
but in case of ICMP, the ICMP is carried out.
Yeah, in case of ICMP, yes. In case of ICMP, yes. But I will not suggest to visualize your analogies, the road, vehicles, and data analogies from ICMP point of view. No, do not think like that. The one that the analogy that I gave is purely for your networking layer.
Yeah, just for understanding purpose. Yeah, I got it.
Yeah, no problem. I mean, it's however you would like to visualize. Yes, but my analogy was purely for network layer and not for any other layer.
Yes, got it, sir.
Yeah, no problem. So again, so whatever application that we are using Zoom. We are reading everything on the Zoom. So our Zoom is basically running on the application layer, which is getting basically encapsulated in all these layers, right? And finally in the data link layer, and through our physical medium, wire or wireless, it's being sent, and on your laptop it's being received and then getting decapsulated at each layer, right? This is how the OSI layer works. Anyway, what I'll do is we'll just take a 5 minutes short break, and then we'll convene back. Okay, thank you. Welcome back. Okay, so Kaush, just hold on to your questions. We'll discuss that in the end, right? Before ending the class, we'll discuss that.
Okay, sir, no problem. Thanks.
Okay, so starting here, starting our discussion, and the first chapter in our CC, NP, Encore, and NRC is that about switching, like how basically. So again, I'll start with the interview question first. Okay, we'll start with switching, and in switching, the first and foremost question that I ask everyone is that how do switches forward traffic? Can someone tell me how do switches forward traffic?
Through VLAN
Okay,
On the
through
basis of
one
the
answer is VLAN,
MAC
other
address
is
of the devices.
MAC address. Okay, any other?
Yeah, switches have a table called as a CAN table, database of MAC addresses, and based on that, it forwards.
Okay.
Using MAC address table.
Okay, MAC table. Then now what is first thing? The moment we say how do switches forward traffic, okay, we need to understand that before even forwarding the traffic, it needs to know or it needs to learn about the traffic. Just like in routing, where it has a routing table, correct? In a router, it has a routing table. And in the routing table, it has multiple entries of the destination networks or the destination IPs, right? And in that, it it is mentioned either the next hop IP or the exit interface, right? So how does the router learn this? Either via static routing, meaning I manually enter the destination network and the destination IP and the exit interface or the next hop IP, right? Then either using the dynamic routing where I use OSPF, EIGRP, RIP, or ISIS to make the router learn about different networks. So similarly, how does switch learn or switch populates its MAC table or CAM table? Can anyone tell me? Before we even go how it forwards the traffic, we should know how. Sorry?
Through the frame that incoming frame of the switch.
Okay, in the incoming frame, there are so many frames that are coming. What does it
checks that which port it is coming from, and it enter into the MAC address table.
Or what does it enter in the MAC address table?
I mean the port number versus MAC and port number and MAC. I mean the what is called MAC address. That Correct. This particular MAC address accessible from this port.
Exactly. So let's say that this is switch 1. Okay, and this switch 1 is connected to multiple PCs. Okay, PC number 1, PC number 2, PC number 3, and PC number 4. Okay, so it is connected to multiple PCs. PC number 4, right? Let's assume that PC 1 has a MAC address 1111. Okay, this is PC number 2. It is 2222. This is 3, all 3s, and this is all 4s. So once, let's say that I want to send a packet from PC number 1 to PC number 2. Let's not involve IP addresses. Let's just think straight just from the MAC address point of view. Okay, just think from the MAC address point of view. Let's not just involve IP addresses here. Okay. Let us also think that all the PCs know about each other's MAC address. We are also assuming that. Now, if PC 1 sends a packet to PC number, let's say 2. Okay, and let me write down the port address.
Well,
port
if
numbers,
they already
1, 2,
know the
3,
MAC address, then there will be no ARP. Okay, the traffic will be directly forwarded to that particular destination.
Correct. Okay, so there are so many hypothetical situations that I'm assuming. Okay, so if see, first thing, if all the PCs know about each other's MAC, so switch 1 has already populated its MAC address table. Correct. So that's why I said I'm taking a hypothetical situation where PC 1, PC 2, PC 3, and PC 4, they know about each other's MAC address, but switch's MAC entry is empty. Switch's MAC table is empty. It does not know. So let's imagine that MAC row or MAC column, and this is the port column. All right. Now, let's say that switch 1 sends a packet or sends a frame to PC 1 sends a packet to PC number 2, right? So the source MAC is 1111. Destination MAC is 2222, right? PC number 1 sends this packet. It reaches the switch and it hits the interface number 1. The moment a traffic hits the switch, what the switch first does is it checks that if the source MAC, if the particular source MAC of that particular frame is present in its MAC table or not. As per our example, switch 1's MAC table is completely empty, right? So switch 1 sees that the source MAC is not present in its MAC table, and it makes a note of it, 1111. And on what interface was it received on? It was received on interface number 1. So it makes a note of it. Okay. And then it sees that, do I have the entry for the destination MAC? Here, in this case, it does not have the entry for destination MAC as well. So what it does, it basically broadcasts it out of all the exit interface. It broadcasts it out of all the exit interface. Now, this packet will be received by PC number 4 and PC number 3 as well. But they will not respond to it because the destination MAC for PC number 4 and PC number 3 is not 2222. So they will basically ignore or discard this packet. Correct? Then PC number 2 receives this packet. It sees that destination MAC is its own. It has to respond. Correct? When it responds, it makes a packet with the source MAC as its own MAC address, that is 2222. Destination MAC is 1111, and it forwards this packet. Switch receives this packet, and it is received at interface number 2. It again, first thing switch does is that it checks if the source MAC is present in its MAC address table or not. It sees that the source MAC is not present in its MAC address table. It makes a note of it, right? And then the second thing it does is it checks if it knows how to reach the destination MAC. Yes, in this MAC address table, it knows how to reach the destination MAC address. If it wants to reach the destination MAC address, it needs to forward it out of the exit interface, that is interface number 1. So it forwards the packet out of the exit interface, that is interface number 1. So here we saw one thing. First is that this is a unicast packet. Correct? This is a unicast packet where there is a source MAC entry. There is also a destination MAC entry. Right? That is what you call it as unicast. Okay. So the unicast forwarding of switch happened when PC number 2 was replying back to PC number 1, where the entry for destination MAC was present. The destination MAC for the destination MAC was present in the MAC address table. So switch 1 knew how to reach the destination MAC address via interface number 1. The frame has a source MAC entry. The frame has a destination MAC entry, but the destination MAC should be present in the MAC address table. Then you call from switch's perspective, from switch 1's perspective, this is called as a unicast forwarding. Okay, this is one. Second is a broadcast forwarding. Okay, a broadcast. This broadcast happened when the first entry, when there was no entry in the switch's MAC table. PC number 1 forwarded this packet. Switch 1 learned about the MAC address. It made an entry, right? When it's tried to find out the destination MAC, it was not present. When the destination MAC was not present, it basically broadcasted it out of all the exit interface. This is called as this is not called as a broadcast. This is called as an unknown unicast. I'm sorry. I would say that as unknown unicast. Unknown unicast. First, why is it unknown? Because it does not know about the destination MAC. It does not know about the destination MAC. But however, the MAC address is a unique, the frame is a unicast. It is intended to go from source to the destination. That is why it's a one-on-one communication, but the destination MAC was not present in the MAC address table. That is why it's unknown, and it's a unicast. The unknown unicast messages are treated as a normal broadcast. They are treated as a normal broadcast, where the switch broadcasts the packet or the frame out of the exit interfaces, or the remaining exit interfaces. Okay, so this is one unicast, unknown unicast, and then there is broadcast. Obviously, there is a separate broadcast packets where the destination MAC has all F in its entry. When the destination MAC has all F in its entry, that's what you call it as broadcast. There is a difference between unknown unicast and broadcast. Unknown unicast are treated as broadcast. However, the destination MAC entry will not be a broadcast entry. It will be a particular MAC address. But in your broadcast traffic, the MAC address will be of a broadcast address. Everyone clear? Any questions? So with this, we learned how these switches learn the MAC address, and also how do switches basically forward the packet looking into the MAC address table. Any questions here? Okay. I'll take that
Well,
as a
is
no.
it not a security concern that the switch is forwarding the traffic to like 3333 and 4444? I know they reject the packet. Okay, the actual destination, the intended destination is PC number 2. So 3 and 4 will reject that. So, but still, the frame will be forwarded, as you said. But it's not a security concern.
It may be a security concern. It may not be a security concern. Okay. The reason it may, yes, obviously, it may be a security concern if I am an intruder. Okay, and there is no security policy involved here. Okay, we are not getting we are not getting in depth about security thing here. But as you said, yes, it may be a security vulnerability as well, where I am intending to send an unknown unicast. Uh, when I'm sending an unknown unicast packet, it is received by all the uh, devices that are connected to the switch. Okay, so yes, that's a security concern. But however,
plus there is a wastage of bandwidth because they have to process as well.
Correct. Obviously, yes, that's a wastage of bandwidth. But you can't do anything. That's how the switches have been designed to work. Just imagine if he's a genuine user and if he wants to connect to PC number 2, right? But if there is our security concerns, right? So security concerns are not basically created on your PCs. Like we'll discuss that later. Like you have antivirus softwares installed on your PCs, etc. We are not getting on that. But inside your network itself, you have security features. You install firewalls, you install IPS systems, etc. to have prevent intrusions. Okay, so again, as I was saying,
that is only in layer 3 switch, right? L3 layer 3 hour switch, not in layer 2, as far I know.
Correct, absolutely. In layer 3 switches only we can have
and in the real
IPS
life
systems.
switch, like there is a multiple ports, not only 4 ports.
Correct.
As you had seen in the picture, huh?
Yep.
And router has less number of ports. Switch
Yes.
has like 48 ports, like
correct.
that.
Yes. So yeah, you are right. I mean, this can be a security vulnerability as well. Okay, people may use this as a security, insecure way of logging into a switch or anything. Yes, but there are to prevent intrusion here. Since this is not a security course that we are learning, we are not going to get involved. But as you pointed out, yes, this may be a kind of vulnerability. Yes.
So, hi, this is Vishal.
Yes.
So, I was thinking of when there is a unicast packet coming from PC1, and when the switch don't have 222 in its MAC table, it does not forward the same frame that came from PC1. It creates another frame asking for who is 2222, right?
Yeah. I did not get there. I said I am assuming, as I said before even discussing that, I said I am doing couple of hypothetical assumptions. Okay, because we have already discussed ARP in the starting of our class. We have already discussed ARP, right? But with the ARP, your switches, the switch will automatically populate the MAC address table. But my intention is not to show you how switch populates the MAC address table using ARP and all. We have already discussed ARP. So I made a couple of hypothetical assumptions where I said that the switch's MAC address table, first assumption is switch's MAC address table is empty. That's first assumption. Second assumption was that all the PCs know about each other's MAC address.
Okay, my question is, does that the same packet is forwarded to all the PCs requesting who is 222, or a new is created doing the unknown
switch
unicast?
basically copies that particular what do you say? Yeah, okay. Okay, I got it. What you're saying. 2222, right? So this same copy, same information is basically copied and sent out to all the interfaces.
Yeah, consider that this packet that came from PC1 with source and MAC source and destination addresses has a data inside it, some form of data it is carrying. So while doing the broadcast, asking who is 222, will the switch forward that same packet with the data or a new?
Yes. No. No. Because it does not have the entry for 2222, and switch's basic function is to broadcast an unknown destination MAC address. Okay. With the intention that since it does not know how to reach 2222, out of which interface should it send? It does not know if this MAC address 2222 resides at interface number 2, 3, or 4. It does not know that. Okay, so it forwards or it broadcasts this exactly the same packet out of all the interface with the intention that whoever has the MAC address 2222 will probably listen to it. And the other devices who do not have the MAC address at 2222, they will ignore the packet.
Okay, got it. Right. Thanks.
Yeah. Okay, right. No problem.
Yeah, I have one question.
Yes.
Yeah, so if we put another switch in place of PC1, so can we draw a diagram so it will be more clear to me? If we place another switch in place of PC1, like there is two switch, and then the one PC is connected. Yeah. So when we ping from this PC to switch one, so first of all, so it will packet go to the switch 2, and then switch 2 will change the packet information, that source IP. It will change its own, provide its own source IP. It will also provide the source. It will own like its own MAC address, right? But the destination will be same.
Give me a minute.
So now this packet will move forward to the switch 1, and when switch 1 will reply, it will send to switch 2. So now how does this switch know that I have received this, and I have to send it to the PC1? Because there is not, I don't think, I don't know the answer of this. That's why I asked you.
No problem. No problem. Okay. It's good to ask question. So now, let's do the same thing. I'm not going to write down their MAC addresses. Let's assume it's 1, 2, 3, 4, 5. Their MAC addresses. These are switches. These are PCs. Okay. Let's assume the same thing. Source MAC is 1, 1, 1, 1. Destination MAC is 2, 2, 2, 2. All right. PC1 forwards this information to the switch. Let us assume that switch 2's MAC address table is empty. Switch 2's MAC address table is empty. So okay, can you tell me your name? Who asked me this question?
Utsav.
Sorry.
Yeah, Utsav.
Okay.
Utsav.
So yeah, thank you. So PC1 sends this packet and it is received by switch 2. Let me note down their interface numbers as well. 1, 2, 3, 4. This is 1, 2, 3. Okay. So switch 2's MAC table is empty. When its MAC table is empty, just now we saw that in its MAC address table, it has to make a note of it, right? So destination, it receives this packet. It sees that the source MAC and MAC entry is present in its MAC table or not. Again, the MAC table is populated using the source MAC address and not the destination MAC address. The MAC table is populated using the source MAC address and not the destination MAC address. So it sees that if the source MAC is present in its MAC table, it is not. So it makes an entry for it, and it was received on interface number 1. Then it sees, do I know how to reach 2222? No, it does not know how to reach 2222. What it does, it will send it out of all the interfaces. Okay, 5 will ignore this packet because that's not the destination MAC. 3 will ignore this packet because that is also not its destination MAC. Switch 1 receives it. Switch 1's MAC address table is also empty. Let's assume. Okay. Switch 1 sees the MAC address table 1111. Okay. Port it received on 1. The destination MAC is unknown for it. So it will forward it out of all the exit interface. 4 will ignore it. And who will respond to it? PC number 2 will respond to it. Okay. When PC number 2 responds to this packet, the source MAC.
No, so the source MAC would be from switch 1. Source MAC would be the port 3 MAC. Switch to port 3 MAC, right? It will not be the PC MAC because
no. You are getting confused between routers and switches working.
Because when the traffic
switches do not change their MAC addresses. It's always routers. Switches do not change their MAC addresses.
So this hop to hop hop to hop is used in routers, right? It's not in switch.
Is not in switches. Okay. Again, there are different kinds of switches: layer 3 switches and layer 2 switches. Okay. Let me complete this, and let me complete this explanation. I'll explain you the other one about your doubt. I know what you're trying to say. Okay. So here, when PC2 is replying, source MAC is 2222, destination MAC is 1111. Okay. So when PC2 responds, okay, so switch 1 now makes a note of the entry, the source MAC 2222. It was received on interface number 3, and now does it know how to reach the destination MAC 1111? Yes, it knows how to reach the destination MAC. It needs to send it out of interface number 1. So this packet is now sent out of interface number 1. Then switch 2 receives this packet. It sees that it has received a packet with a source MAC of 2222. Okay, and at what interface? Interface number 3. Right, and it reads the destination MAC. It sees the destination MAC can be reached or can be sent out of interface number 1. So it sends this packet to PC number 1. Okay, here there is no change of your MAC addresses. It's I'm muting you for some time, right? Okay. Then the confusion that you have is, let's say that this is one whole big network. Okay, this is one big network, and it's the network, let's say this network's IP address is 192.168.1.0/24. That means the PCs inside this network or the hosts inside this network will have an IP address starting from 192.168.1.1 till 192.168.1.254. These are the usable range of IP addresses. Now, here is a router. Okay, here is a router. And all these PCs are connected inside. There may be multiple switches or one switch, anything, whatever you want to assume. Okay, and this router connects to one of the switch. The switch is then connected to multiple switches like this, and these switches are connected to the PCs. The change in MAC address will never happen inside this network. The change of MAC address will never happen inside this network. It is always going to happen between the routers that is connected here. So this is router 2, this is router 1, and let's assume that there is a PC connected here. Okay, so if this PC has an IP address 192.168.1.1 and has a source MAC, okay, and has a source MAC of, let's say, 1111. Okay, and it needs to reach this PC whose IP address is 172.168.1.1. Okay, it will send an ARP. R1 will reply for the ARP using the proxy ARP, because ARP cannot go out of its own network, cannot go out of its broadcast network. It will not go towards the other PC. So what happens? The MAC address for this destination IP, right? I am trying to ping. Assume that I am trying to ping from this PC to this PC, right? So what happens? The source IP is 192. The destination IP is 172. There will be a source MAC. The source MAC will be PC1's MAC address 1111. The destination MAC, to resolve the destination MAC, PC1 will generate an ARP, but the ARP is going to be received by everyone inside this network, even the router, that is R1. That is its default gateway, right? So R1 is going to respond with a proxy ARP, because R1 cannot forward. That is the rule of ARP. ARP cannot go outside its own broadcast network. So R1 has to respond with a proxy saying that is, let's say, that is 2222. Now this PC sends the packet to R1. R1 in its routing table checks the destination IP address. Okay, R1 checks the destination destination IP address. It finds out what should be the next hop IP, what should be the exit interface. Using that, okay, remember when R1 received the packet, this was the information present. This was the information present. Now when R1 is forwarding it, okay, the source IP remains the same, that is 192. Destination IP is 172. Source MAC. Now the source MAC is going to be the MAC address of the exit interface of R1. Okay, let's assume that the MAC address here, this is 3333, right? That is going to be the source MAC, 3333. Destination MAC is going to be the next hop IP's interface MAC address. That is this one. Let's assume that that is 4444. Here that 4444 entry would be made, and this will then be forwarded to R2. When R2 receives it, R2 will also do the same. It checks the destination IP, right? It makes the calculation of how to forward it. When forwarding it, it will change its MAC addresses, right? So let's assume that that is 5555. Then PC, this particular PC's MAC address, let's assume that that is 6666. This is how it is going to change network. It's not going to change the MAC addresses. Clear, Utsav?
Yeah, so I was in doubt that source IP also going to change on the routers, right? So now I got to know that only MAC address is changing. Yeah, okay.
Source IP never changes. See, inside
So I thought
inside the same network, MAC addresses are not going to change. Okay, and when the routers are forwarding information from one hop to other hop, the source IP, destination IP remains the same. Only the MAC addresses will change. As you see here.
Thank you. Doubt is clear.
Yeah, no problem.
Yeah.
Anyone has any other question with the switching here? No. All right. Next, coming to the topic of our VLAN. My understanding of VLAN is that, I'm sorry, my understanding of what VLAN is that, let me go back to history, okay, of why and when were VLANs created and why and how were they created. My assumption is that, and this is all theory that I think may have come up. The computers were created. The computers were created to do faster mathematical calculations. That was the main purpose of the computers, to create, to do mathematical calculation faster than human beings, right? So that was the main purpose of the computers to be created. Then what happened, as more and more computers started to come up, started to be invented, people thought that let's exchange the information between these two computers so that we can collaborate and we can do the mathematical problems even faster. So what we did, we started to connect these two computers, okay, and they started to exchange information. Then what happened is that when these two computers started to exchange information, again the need come up that more and more computers need to be connected together, right, so that they all can exchange information. Let's say that this is a defense organization and they need that all the devices are able to exchange information with each other, right? So if there are 4 PCs, one PC has to be connected to all the other 3 PCs. So there should be 3 ports. There should be extra 3 ports so that the PC can be connected. It's not, I'm using the word PC and the computer interchangeably. So just ignore that. So if the PC wanted to talk to other PCs and exchange information, it needs 3 extra ports. With just 4 PCs in the environment, we needed 3 extra ports on one particular PC. Let's imagine that there are 100 PCs or computers, or let's imagine there are 1,000 computers in the environment. We need 999 ports on one single PC. Okay, so back then it was difficult. It's not like it was impossible. It cannot be done. There can be computers created. Back then the computers were giant. You can create multiple ports and connect different cables into them and connect 1,000 computers. It's okay. But then it was a tedious task. Correct. It was a tedious task, and nobody was really had the time to create a computer with 999 ports and connect them. And it's not like all these 999 computers are in the same geographical location, meaning that they might not be in the same area. Some might be 50 meters away or 100 meters away, something like that, right? So creating 999 ports and creating such length of cable so that the computers that are 100 meters away can be reached was difficult, right? So what they did, they thought of creating a device which basically would help them to copy and duplicate. Copy and duplicate are both the same thing. So duplicate that particular information that one computer creates and send it to all the other computers. That first unintelligent device was called as a hub. Right? So all these computers will be connected to the hub. Let's say PC 1, 2, 3, and 4. So when PC 1 sends an information, it reaches the hub. The hub duplicates the copy, duplicates that information, creates multiple copies of the same information, and forwards it to the other PCs connected here. Okay, and what happened? All you need to do was, if you want multiple PCs to be connected, all you need to do is create a hub with multiple ports, right? And if any one of the PCs is trying to connect or trying to send some information, it will be sent to all the PCs that are connected to the hub. Okay. Then there was a need that came up where they said that I do not want PC 3 and 4 to listen to my information because it's not necessary for it or it's confidential, anything. What can be done? I cannot use a hub. because if I send any information to the hub is going to duplicate it and send it out to all the ports, out of all the ports, right? I do not want that. So I created a switch. This switch was the first intelligent device which basically sends out information based on the based on some information, and that information were the MAC addresses. So the switch basically reads the MAC addresses and forwards it to the intended destination, right? So then what happened? I created MAC addresses. I gave MAC addresses to all these PCs, and I said if PC1 wants to talk to PC2, all it needs to do is that it needs two information. It needs to have a source MAC address, then it needs to have a destination MAC address. Using these two information, the switch can then forward the packet to the intended recipient, right? So if PC1 sends this packet to the switch, switch reads the destination MAC, forwards it to PC number 2, right? That was very simple. Now just imagine that, create this into a whole big environment, big whole campus. So you have multiple switches, switch number 2, switch number 3, okay. And here you have multiple users connected. User number 5, user number 6, user number 7, user number 8. Here also you have user number 9, 10, 11, and 12. Okay, so you have multiple users that are connected to them. So what happened? If let's imagine that, let's think of this as a college campus. Okay, PC1, okay, he's a mechanical teacher. Okay, mechanical department teacher. And PC number 5 is also a mechanical department teacher. But inside the campus, they are sitting in different buildings. Okay, they are sitting in different buildings. Now, PC number 1 decided that he wants to send the information. He tend to share the question paper. He needs to share the question paper to PC number 5. What he's going to do is he's going to write down the source MAC address. He is going to write down the destination MAC address and forward it. The switch will then forward it to the PC number 5 based on the destination MAC address. Pretty clear, simple. But then let's just imagine they're not just one mechanical teacher. There are hundreds of mechanical teachers. PC 6, 7, 8, 9, 10, all of them are mechanical teachers. So what will PC1 be doing? Will he be writing down destination MAC address one by one and hoping that this switch will just forward it? So what if there are, let's say that if there are 100 mechanical teachers, the PC number 1 or the question paper 99 times to each of the mechanical teachers, right? That was again a problem. That was again a problem. So what we did, we came up with a solution for VLANs, where VLANs stands for virtual LAN. Okay, we came up with a solution for virtual LAN. When virtual LANs started to come up, what happened? We said we divided these, taking the department of mechanical. The mechanical department was then given a VLAN number. We'll discuss VLAN in length, but I'm just giving you an overview. So VLAN, let's say that VLAN number 10. Okay, the mechanical department is given a VLAN ID, that is VLAN number 10. So let's imagine that 6, 7 are also mechanical teachers, right? So PC number 1 is a part of VLAN number 10. PC number 5 is a part of VLAN number 10. 6 is a part of VLAN number 10. 7 is also part of VLAN number 10. Okay, so what happened is, if PC number 1 wants to share information with the mechanical teachers, all he needs to do is he needs to add another information saying that the VLAN that all these destination MACs belong to are VLAN number 10. Now, what the switch will do is, switch will Now, instead of checking destination MAC, he will also be checking VLAN numbers as well. And he will forward those information only to those devices that belong to VLAN number 10. So when this particular question paper reaches switch number 3, it is going to check VLAN number 10 devices or MAC addresses, and it will forward it to PC number 5, 6, and 7. And I think that's how your LANs VLANs were created for this purpose. Okay. Just one question. Gaurav, what is the length of the class? Just wanted to know.
Sorry?
What is the length of one class duration? Is it 2 hours, 2.5 hours?
Yeah, 2 hours.
2 hours. All right, no problem. Thank you. So with that, I think now you know the history of VLANs. With that, before we get inside the discussion of VLANs, I would like to ask you one question about VLAN. Pay attention to the question, and it's an interesting question. Okay, if two PCs connected to different switches, connected to access port, connected to access ports of different switches. If two PCs connected to access ports of different switches, and the link between the switches is not a trunk, okay, can the two PCs communicate? This is the question. Read the question carefully.
Yes, they can communicate.
Okay, I'll come to the explanation later.
If it is same VLAN, it will communicate.
If it has the default setup for the both switches and both same vendor, it will communicate.
Unless you don't configure any trunk, okay, the VLAN tag will not be attached with the frame, and therefore, I mean, between the two switches, you should configure trunk, but you didn't do in this case. Okay, so unless you don't create any trunk, so VLAN tag will not be attached. So this is the concept of native VLAN. So therefore, these two pieces can communicate. Of course, they can communicate.
Okay, one says yes.
Yes.
Okay,
So,
again,
let
me no. Let's you guys just think about it for 5 minutes, right? So as the question says, if there are two PCs, again I mentioned different access ports. Okay, so let's draw two PCs, PC number 1 and PC number 2, and says connected to different access ports of different switches, right? So switch number 1, different switches, right? So and switch number 2, and it has been mentioned two different access ports. Okay, access ports meaning the assumption is that this is part of VLAN number 20, this is a part of VLAN number 10, and the link between the switches is not a trunk. If the link between the switches is not a trunk, this is also part of VLAN number 10, and this is also a part of VLAN number 20. Can the two PCs communicate? Let this IP be 10.0.0.1. This guy is 10.0.0.2. Now I give you 2 minutes.
Yes, it will.
Okay, so
I think
okay.
It will not
Give me a
communicate.
minute. Hold on. Just a minute. Hold on. Whoever is saying no, please raise your hand. Okay, so I'm writing down your names. Okay, just Do not mind here. Where is it? Okay, so please raise your hand. Shah, Rajendra, there's Anil, Shlok, what's up? Shlok, what's up? Okay. Anyone else who says it's not going to work? I mean, do not think that because I said no, that means you guys are wrong. No, I am just noting down the differences here. Anyone else who says it's not going to work? Okay, on the chat. All right. And now, okay, please put down your hands. Please lower your hands. All right. Now, whoever is saying yes, please raise your hand. Okay. So, so these are the names. Let me just bring them closer. All right. This is one of the common. Okay, all of you can just put down your hands. So this is one of the most common interview question that is usually asked. If two PCs are connected and they are part of different VLANs, and they are connected through two switches, and the link between them is not a trunk, can the two PCs communicate? This is a very common interview question. I'm not going to say if it is a yes, if it is a no. I'll just start to explain, and then you can find out if you were correct or not. Right. So I hope I can finish this in 2 hours. Okay, and on the chat. Okay. Yes, if they are in the same VLAN. Though, see, here it says they are not in the same VLAN. So basically, your answer comes into the no side anyway. Right. Now, let's say that I do a ping. Give me a minute. Let me remove something. Okay. Let's think that if I do a ping from the PC number 1, ping 10.0.0.2. If I do a ping, what is going to happen is that a source MAC is going to be created. A layer 3 header will be created with source IP, destination IP. A layer 2 header will be created with source MAC, destination MAC. Okay. And then what happens? This PC is going to be, this PC forwards the packet to the switch number 1. Switch number 1 receives this on the interface, and that interface is configured as an access port for VLAN number 10. Okay. So, and then it sees that which are the other interfaces which are part of VLAN number 10. Okay. And it forwards this packet to switch number 2. Switch number 2 will receive it, will accept this packet. Okay. Why? The reason is that because these two interfaces are configured as access ports. Okay. These two are configured as access ports. Whenever you configure the switch as access ports, there are no VLAN tag on your layer 2 header. There is no VLAN tag on your layer 2 header. Access port means that by default, the switch thinks any traffic that is being received or being transmitted, okay, is a part of VLAN number 10. It's like, it does not need any confirmation. Whatever traffic is being received or being transmitted out of that particular interface has to be part of VLAN number 10. That is what access port means. Okay, so there is no VLAN tag on this packet that is being sent by switch number 1. When switch number 2 receives this packet, because it's an access port, on this particular packet, the ping packet, there is no VLAN ID mentioned. Since there is no VLAN ID mentioned, switch 2 assumes that whatever packet is being received on the access port has to be a part of VLAN number 20. Has to be a part of VLAN number 20, and it forwards this packet to PC number 2. PC number 2, when it responds, okay, this packet is received by switch number 2 on the access port. On the access port, when it is on the access port, again, switch 2 does not tag it with a VLAN because it's access port. So it thinks whatever, again, the same concept, whatever traffic is being received or is being transmitted has to be a part of VLAN number 20, and I do not need to specifically tag it. I do not have to specifically tag it because it's an access port, and it sends out an untagged packet to switch number 1. Because switch number 1 receives it on the access port and it does not have any tag, it's an untagged frame. It is an untagged frame. Switch 1 accepts this packet because there is no mention of VLAN ID. Because there is no mention of VLAN ID, switch 1 assumes that it's a part of VLAN number 10, and switch 1 forwards this to PC number 1, and hence they will be able to communicate. Yes, there is definitely a VLAN mismatch if CDP is involved. If I ignore or if I disable CDP, there will be no VLAN mismatch syslog that is created. CDP is for Cisco's devices. So since we are learning from Cisco's point of view, yes, you will see a VLAN mismatch, syslog being created. But if I disable CDP, I will not see the VLAN mismatch. Even with a VLAN mismatch, syslog, they will be able to communicate. Okay. Now, when will there be a VLAN tag? When will there be a VLAN tag? The moment I hope you guys know how to add VLANs to a switch port. It's like interface. We go into the interface configuration and we write switch port access mode VLAN number 10. Right. If it's a trunk port, when we configure this port as a trunk port and this port as a trunk port, the movement on the switch, be it on any interface, the moment there is a trunk configuration on the switch, all the access ports will have VLAN tags. All the access ports will have VLAN tags. If there is no trunk config, if no trunk, let me again write that down. If there is no trunk, no VLAN tags. Okay. If there is trunk, then there are VLAN tags. This is the basic understanding that we need to have. Since, as I said, these two switches are not a trunk link, that's why there will be no VLAN tags. Okay. The moment I create this port as a trunk port, this port as a trunk port, then let's take that example as well. So this I say as a trunk port, and I allow VLAN number 10 and VLAN number 20. The same thing I do here. I configure the switch to as VLAN trunk port, and I allow VLAN number 10 and VLAN number 20. Now, when the ping goes, switch 1 then sees that at what interface was it received and what VLAN is that a part of. It sees that that interface is a part of VLAN number 10, and then you will have a VLAN ID tag. Okay, that's basically your TCI ID in your Ethernet header. I'll show you that in the practical tomorrow. Okay, so today just we are going to discuss this thing. So it's called the TCI ID, VLAN number tag. And with that VLAN tag, okay, why do we need a VLAN tag? Because it's a trunk port. Okay, again, there is a difference between access port and trunk port. On your access port, you can only send one VLAN. It can be any VLAN. On that particular access port, you can send only one VLAN. Since you can send only one VLAN, there is no need for you to tag it, because any traffic that is going to enter or exit out of that particular port is going to be the part of that particular VLAN. But with the trunk port, there are multiple VLANs that you can pass through that interface. So if your traffic is not tagged with a VLAN ID, how will the switch determine which VLAN does that belong to? That is why whenever you configure a trunk port on the switch, it starts to tag the VLANs. It starts to tag traffic with the VLAN. So here it has tagged it with the VLAN ID 10, and since we have allowed 10 and 20 both through this interface, it goes to the switch. The switch reads the VLAN tag as VLAN number 10. VLAN number 10. Okay. Now, anyway, PC number 2 in this scenario will not be able to receive it because this is a part of VLAN number 20. If there is any other PC, let's say 10.0.0.3. Okay, here 10.0.0.3. Let me change that to 10.0.0.3 here. Okay, then switch 2 sees which is the interface that is a part of VLAN number 10, and it will forward it to PC number 3 here, which has a VLAN IP of 10.0.0.3. In our original case, where this was 20, okay, and this was just 2, switch 2 will receive it. It see that it's a VLAN number 10. Okay, it's a VLAN number 10, and it will see that there are no ports. There are no ports with which are part of VLAN number 10, and it will drop it. It cannot forward it. It cannot forward that packet, and probably that this PC is never going to even receive that ICMP packet, because it's a part of VLAN number 20 and not a part of VLAN number 10. So switch 2 will never forward this packet out of this interface, and the ping will fail here. Any questions?
I have one question, not in this one, but the previous diagram that you drawn. Can you please go back to the previous diagram of the VLAN?
Let me do that. Yeah.
No, not this one. The multiple. I mean the diagram that you explained before. Scroll, go to the left. Not this one. Yes.
Okay.
Yes,
Okay.
yeah, exactly. Okay,
yeah.
So we basically know that, yeah. So what happened here is in the switch, the different end hosts are connected, right? And we basically know that so first of all, this switches, of course, should be access layer switch, right? Access layer.
Yes.
But we basically know that if you saw campus layer architecture, like enterprise architecture, the access layer switches are not connected together. They should connect it to the aggregation switch, but aggregation layer the switches are connected together. But access layer switch, if you see campus layer architecture, they're not connected together.
Correct.
So you understand my point? So
yes. Okay. Yeah. I mean, I understand your point,
here,
but what is your question here?
So in that case, I mean, how this type of topology fit into the? I mean, So why you
This is
connected the
see,
two? I understand.
this is just from a explanation point of view.
Okay,
Okay, this is
but
not.
in the
It is not from a real time point of view. Okay, of
okay,
course, in real time, the connectivity design. There are a lot of design things that you need to keep in mind before you even try to
mhm.
implement it in the production. Okay, this is just from
Okay,
an explanation point of view that I am
okay.
doing.
Because basically we know that the switches are connected together in the like access layer switches are connected to the aggregation switch
Correct.
distribution. Yeah.
Hmm.
So all this concept, this one, trunk port, ether channel, all these concepts coming this layer when you join these two switches, two
Correct.
different layers.
Yes. Yes.
Okay, that's my question. Thanks.
All right. No problem.
So, can we get to know the what are the all the topics which we will learning here? So, this is
Okay.
the just switching concept, right?
It is just a switching concept because the first chapter is about forwarding in switching and routing. How switches basically forward. Okay, give me a minute. So these are the from Encore point of view. Just check. From architecture, give me a minute. Hypervisor, this one, infrastructure. Yeah, this is the infrastructure layer 1, layer 2, layer 3. So right now, our first chapter basically involves the trunking. I don't have the. Let me quickly check if we have the PDF. Can I find a PDF?
So, we will like you will be teaching us the whole syllabus, right? What is written there in the Cisco side?
Yes, yes, yes.
Okay.
And guys, this is going to be a not only Encore, it's going to be a Encore and RC both combined routing switching. Because in Encore there are some topic which is just explanations, but in NRC it's in depth. So the approach what we guys are gonna follow for this batch, if in case anything related to like an introduction, we'll start with introduction and we'll deep dive to the configuration and troubleshooting at the same time.
Okay.
So you mean Encore first and then NRC? Is it
No,
how it
I'm
is
going
going?
to
Like
Just
both.
just
yeah,
Encore,
both.
right?
It's
Okay.
both, as he's saying, it's both.
And even
Because
this is not
NRC,
only for a CCNP, it's like a CCNP to CCI concept, like a technology classes.
yeah. So here, if you see, we discussed today. What we were discussing was the chapter 1. Sorry, without mouse, it's difficult to do that. So here, if you see here, we were discussing few things: LANs, access port, trunk ports, how forwarding happens in layer 2. We discussed a bit about what is layer 3 forwarding, right? What is IP addressing? We'll talk about IP addressing, assignment, all those things. So I'm going chapter wise. So today we just discussed an overview of the first chapter. So tomorrow we'll get in a bit of a depth here. So this is your encore. So this this is your encore, where you have switching and routing both. But in your NRC, you will only have NRC is called as Enterprise Advanced Routing and Switching, right? So they advanced routing technologies. So there you'll only find routing technologies like OSPF, BGP, EIGRP, etc. But Encore encompasses both. Okay, so we'll be looking into NRC and Encore both and in depth. And let me also tell you that your CCNP, okay, your this Encore, okay, people who might like to know this, you have two types of.
So we will be going in depth of VXLAN list, all these topics also.
Is it there? Did you see? I'm not sure.
VXLAN is part of data center.
Yeah, VXLAN is a part of data center, but I'm just
No,
checking if it's there
so
in this.
no,
I'll
there
go
was mentioned
properly.
it was in the 606.
RSTP.
I think VXLAN is a part of data center.
Yes, it's a part of data center, but sometimes they do involve a few topics of VXLAN.
Yeah, so it's written above this infrastructure segment above. So it's written above on the top, Lisp and
Yeah.
VXLAN.
It's from a virtualization point of view.
Yeah.
Okay. Yeah. Describe virtualization concepts. Yeah, we'll discuss a bit about